Hello and welcome to this Feature of the Week video. This video is the second part of the modeling of categorical data. You will find it helpful if you want to learn how to fit a structural model to categorical data, or if you develop a good model and you ask yourself how to use it further and interpret the results. You will see a concrete example with typical features of categorical data and models. But of course, you can generalize the approach I present today to other cases. Before we start, this video is for users who have a basic knowledge on categorical data. So you should know what it is, what are typical models, and how to write them in the Mixtran language. If you don't know it yet, I recommend you to watch first the previous video on categorical data number 140. So learn the theoretical basis and then come back here to see how it works in practice. The case study I use in this video is about patients with knee pain. Part of them received a treatment and the rest is in the placebo group. At 4 different days, they assessed the level of knee pain in the scale from 1 to 5. So 1 corresponds to no pain and 5 to the most severe pain. This is a categorical ordinal data because pain levels are ordered. One of possible goals of the analysis is to assess if the treatment is effective. To do that, we need to first find a good structural categorical model which captures well the observed data. Then we can analyze the covariates and test if adding treatment has a significant effect on individual parameters. In this MonolX project, I already loaded the dataset and tagged all columns. I remind you that when you use categorical data, you need to change here the data type from continuous to categorical and count. The observed data plot shows you the observed pain levels. If you hover on any individual, you will see how it changes over time. The stacked view option shows data as a distribution at each measurement time point. I add legend to see which color corresponds to which level. In this plot, you can see the decreasing number of individuals with high pain levels. As usual, I can split this plot in the stratify between different covariate groups. Because we want to answer if a treatment is effective, I split this plot by a treatment group. Placebo group is on the left. We see that there is an improvement in both groups, but the effect seems to be stronger in the treatment group here on the right. Let's define now the structural model. First, a short reminder on the Mixtran syntax for categorical models. Model definition has to be in the definition block. With the argument type, you specify that the model is categorical and not count or time to event. Then you define the list of all possible values. It can happen that there are more possible values than the values measured in the dataset. You need to define probabilities only for n-1 categories. Definition of the last category is implicit because all the probabilities sum to 1. You can write the model directly with the logit function. It has values from minus to plus infinity, so it is more convenient from the point of view of estimation of model parameters. Finally, for ordered categories, you can use cumulative probabilities in the definition. Now let's go back to our example. Pain levels are ordinal categorical data, so the model describes cumulative probabilities. And also I use here the logit function. The constant probabilities give the simplest model. It is helpful to write alpha 1 plus alpha 2 for the probability of being level 2 or less. It ensures that the probability to be 2 or less is higher than the probability to be 1 or less. However, the constant model in this case is not a good choice because he observed that the pain levels decreases over time. So to model it, I add terms that depend on time with additional parameters gamma. In general case, there is one parameter gamma for each cumulative probability. The proportional odds model assumes the same time dependence for all cumulative categories. So in this case, all gamma parameters are the same. Remember that T is the Mixtran keyword for time. I will first try this model in monoliths, but before we go to monoliths, we have to look at the individual model. To meet the assumptions of the model, the individual parameters have to satisfy certain conditions. First, the logit function ranges from minus to plus infinity, so the parameter alpha can be positive or negative. For custom models, monolith assumes that all parameters are positive and by default sets the log normal distribution. In this case, we need normal distribution, but we can easily change it in the statistical model tab before the estimation task. Then, to meet the cumulative probabilities assumption, parameter alpha2 has to remain positive. This will assure that the baseline for the levels equal 1 and below is lower than the baseline for levels equal 2 and below. The same positivity assumption holds for alpha3 and alpha4. Parameter gamma describes the dependence on time. In a general case, it could be either positive or negative. But let's see if we can say something more in this case. So let's look at the cumulative probability for level less or equal to 1. Data shows that the number of individuals with pain level 1 increases over time. We know that logit is a monotone function. So if probability P increases over time, then the value of the logit has to increase. To preserve it with our model, gamma has to be positive, and we can keep the log normal distribution that is selected by default in monoliths. I loaded this model in the structural model tab. To make the code more readable and less prone to errors, I use the intermediate variables LP1, 2, and 3. So at each level, I take the previous level value plus a new term. After loading a model, you need to change the distribution of individual parameters. So I go to Statistical Model and Task tab. Here, you select a normal distribution for alpha1 parameter. And what about the random effects? I keep the random effects for the alpha1 parameter and remove it from other alpha parameters, because alpha1 is present in the definition of each cumulative probability. I also keep the random effects on gamma because the dependence on time can vary between individuals. Now we can go back to the Initial Estimates tab and run the auto-initialization, and then go to Statistical Model and Tasks, select all tasks, and run this scenario. The next step is the assessment of the goodness of fit. In the results, standard errors of population parameters estimated are low, which means that the confidence in the estimation is good. Omega for alpha1 parameter is a number much larger than 1, but this is not a problem. Alpha1 has a normal distribution, and in this case, omega represents the standard deviation and is of order of alpha1. Let's check now the VPC plot. It shows the time evolution of the probabilities for different pain levels. I changed the layout here and set the same limits for the y-axis. Each plot corresponds to a different pain level. The blue line represents the percentage of individuals with a corresponding pain level in the dataset at different time points. The blue band represents the 90% prediction interval of the same percentage calculated on 500 simulated dataset. We can see that the model captures well the decrease of the probability for level 4 and 5, but the approximation for level 1 and 2 is not that good. To capture better the observed data, we can try different time-dependent functions. So far, I have used a linear model that I plot here with the blue line. I could also consider a nonlinear evolution over time. For instance, a log function or exponent function that I plot here with dashed lines. They give opposite behavior for low and high times. The VPC plot with these models are not better, and the BIC criteria increased compared to the linear model. So what are the other options that we have? You have to remember that any model is based on certain assumptions which may not hold. In this case, A strong assumption is the proportional odds model. It means that we use the same gamma parameter for the time dependence at each level. So what if we remove this assumption and use different gamma parameters? In this project, I use a model with 4 different gamma parameters. I have already run the parameter estimation and generation of plots. The VPC plot shows that this model describes better the data, especially for levels 1 and 2. But let's check the estimated parameters. The standard errors for gamma 3 and gamma 4 are very high. Also, the condition number of the Fisher information matrix is high. These two aspects show that not all parameters can be well identified. This model assumes different time dependence for each cumulative category. But only parameters gamma 3 and 4 are not well estimated and have high standard errors. In this case, we can try to keep the proportional odds assumption only partially. For example, we can distinguish between probability to have a pain below or equal to 1 from all others. It means keeping only parameters gamma 1 and gamma 2 that I have in this model. The resulting VPC shows that the model predictions are good and parameters are estimated with high confidence. So let's look in Sycomore on these 3 projects. Adding 4 gamma parameters gives a better likelihood that we can see here. And we saw that the model without the proportional odds assumption gives better VPC plot compared to a model with a common gamma. But when we correct the likelihood by the number of parameters, so we look at the BIC criteria, then we don't see the improvement. On the other hand, the model with only gamma 1 and 2 parameters gives the best likelihood and the BIC. I'm confident with this structural model, and now let's look if covariates have a significant effect on the parameters. So let's go back to the MonoX projects with a partial probability odds assumption model. Statistical tests include the Pearson correlation test. It checks if the relationship between random effects and continuous covariates are significant. P-values in red and orange indicate that there is an effect of treatment on parameters gamma 1 and gamma 2. These parameters could be correlated. If yes, the proposal will take this into account. Let's check. Indeed, it suggests to add treatment only to the gamma 2 parameter. Pearson test indicates also adding H1 alpha 1 parameter, which is the baseline pain level. It does make sense from the biological point of view. In this Sycomore project, I compare different covariate models. We can observe that effect of treatment on the gamma 2 parameter, which is here, decreased the BIC criteria by almost 50 points. Then adding H on alpha parameter leads to a marginal change in the BIC, which we can see between these two models. But treatment on both gamma parameters gives a worse value of the BIC. I showed you here a stepwise approach to build a covariate model, but you could also run the automatic covariate model building that you can find here in the button Run. Check a dedicated feature of the week video if you don't know how it works. So, using modeling, we answered that the treatment has an effect on the pain level. Now, with the parameters estimated by Monolix, we can quantify this answer. For instance, we can calculate the probability of different pain levels with and without treatment. So let's calculate the probability of having a pain level lower or equal to 2 after 2 weeks. From the model, we have this relation for the logit of the probability to have a level pain 2 or below. After transforming the logit function, we obtain this formula, and it is equivalent to this one. The individual parameters in this formula are the following. Alpha 1 equals the population value plus the effect of age. Alpha 2 and gamma 1 have no covariates effect, so they are equal to population parameters. And gamma 2 includes the effect of treatment. For simplicity, I take a typical individual, so there are no random effects. To calculate the probabilities, we input in these formulas the parameter values estimated by Monolix. So for someone with age 42, we obtain that the full recovery is if the treatment is applied and the probability of pain level 2 or below is at 52% in the absence of treatment. In this example, we analyze if the treatment has an effect on the pain level, and we obtain the answer yes. Remember that you can use a similar workflow to study other problems, for example, joint PK, categorical models, binary data, or nominal categories such as choice in the questionnaire. Thank you for listening and have a good week.